Let's say that you want to catch a lightning bolt. But what is it? Well, it's electricity jumping directly through the air. There is no definitive data, but from what I was able to find, current can reach 200 kiloamps and up to 1 gigavolt. A single lightning strike can last up to 200 milliseconds. Now let's assume for a moment that we know where it's going to hit. Is it even worth the effort? How to calculate that? Well, we need to multiply current through voltage through time. That gives us 11 gigawatt hours of energy, and times, let's say, 50 cents, $5 million. That's nice. Bear in mind, this is the best case scenario. How to store all of that? We can use traditional lead-acid batteries. So we need 4.2 million pieces of these, worth roughly $840 million. Second thing is that it's rated for 1.3 kiloamps of discharge current. If we divide, that gives us 150. We need at least 150 connected in parallel, but at 12 volts. If we divide our 4 millions, that gives us 28,000. Connecting that in series allows 336 kilovolts to be applied. Not enough. Let's start with the voltage. Dividing 1 gigavolt through 12 volts gives us 83 millions. That's not going to work. How about lithium ion? I found Sony 3.7 volts and 3200 milliamp hours. It can go up to 80 amps, that's discharge, but I'm gonna go with that. Dividing that gives us 2500 connected in parallel and an average voltage of 6.2 kilovolts. That's a lot. 1 gigavolt divided by 3.7, that's 270 million batteries. And that's assuming all of them are connected in series. Multiply by 2500 and by $2 each, that's more than $1.3 trillion. Maybe supercapacitors. I was able to find ones rated for 2.7 kiloamps and 3 volts. Dividing that gives us 74 in parallel, 171 kilovolts, too much. And again, starting from voltage, $1,250 billion. That's a lot. Clearly, voltage is a problem. There are also traditional caps like ceramic. Dividing 1 gigavolt through, let's say, 50 volts, that's 20 million connected in series. Using the above formula, we can calculate that every single one needs 0.8 milliamps of current. Let's divide and multiply all of that. Even assuming 10 cents each, that's a lot of dollars. One last option are electrolytic caps. Yeah, 2 trillion. That's going nowhere. We should be more reasonable and take less extreme example. Let's say 100 kiloamps, 100 kilovolts and 1 millisecond of time. That gives us 10 megawatt hours of energy and $5,000 to earn. Lead-acid batteries, $120 million. Lithium ion, 66 million. Supercapacitors, 65. Ceramic caps, 250. Electrolytic caps, 100k. That's not bad. We can clearly see that it would take at least 20 lightnings to make this viable. I'm talking storage only.